Okay, so I should be recording. I see the thing saying red. So hello everybody who's watching this video. Whether this be uh Madeline, Dominic, San, Chantel, anybody else who has this Google Drive. So this is going to be the quick and dirty method of getting all these questions done in the chemical engineering practice exam. In other words, if you really want to fucking pass this thing, you watch this. If not, you don't. So with that being said, we're going to try popping through every single one of these with the allotted time I have. You might hear some dogs in the background. I try to keep them quiet, but right now my mom and sister are out and they're just in the kitchen chilling. They have no reason to be crying. They have food, water, and everything. So they're just being little babies because they're puppies and they hear me talking to nobody. But with that said, it's time to get started. The first question says there's three lines defined by three equations. You see all three equations here. So what's the simplest form of doing this? Well, you take all three equations. You see x plus y equals 0. You turn that into y equals negative x, you see x minus y equals 0, and you turn that into y equals positive x, and you also see 2x plus y equals 1, and you can just turn that into negative 2x plus 1. And then there's two ways of going about this. Method one would just be the simplest. You graph all of these and see where they all intersect by seeing where the lines of intersections are. You could also do it another way where you set them equal to each other and solve for the intersections. I did a simpler way of the two. I just plugged it into a graphing calculator, solved for and saw where they cross intersections with, and they cross intersections at 0, comma 0, 1/3, 1/3, and 1 minus 1. Excuse me, 1 comma negative 1. It's a little dirty because I have the little y comma sort of s. Now, with that said, we're going to go to the next question. Next question is going to be, which of the following is the general solution to the differential equation and boundary conditions show below? Well, this is another one that I really like, and I think I could just do it all here. Yes, this is a good one because you have to know a lot of stuff from differential equations, but since it's a homogeneous just differential equation, in other words, it's just equal to 0, what you could do is that everywhere you see a differential equation, you sub it out with m, and anywhere you see a plus 5, it just or a plus 5y, it just turns into a regular number. The beauty in this is that it just simply becomes algebra. And in the plus 0 stays as equals, excuse me, the equal 0 stays equal to 0. Now, the beauty to this is that you could then go and say m equals negative 5. But this isn't the whole story because that's not the final answer. You have a differential equation, you don't just solve algebra, right? So the general solution, which you can find in engineering handbook or any differential equation, something that looks like this, would be y equals c e to the negative bt, sort of like you saw in class. And the beautiful part to this is that you have m, which would be that b term up here, so negative negative 5, and you end up getting y equals ce negative negative 5 is positive t. Now, with that said, you're still not done because you don't know the final solution, but you do have initial conditions, which you just simply plug into this solution that you solve for, which then would be 1 equals e to the negative, excuse me, to 5, comma 0. Anything to the 0 power, ladies and gentlemen, is equal to 1. Anything to the 0 power to itself is equal to 1. So in other words, this simplifies into 1 equals c. And if c is equal to 1, your final answer is then going to become e to the power of 5t, which simply ends up becoming answer A. Nothing crazy. So we're going to clear the screen, clear all my drawings, and scroll down. So we continue and we go to question number 3. Suppose there's f of t to the power 2. The area under the curve is 0 t to 2, estimated by using the trapezoidal rule with a delta t of 0.5, and you're asking find the area under the curve, basically. Well, it's on you to remember, well, shit, what does that even mean? Well, a smart guy is going to say, it's pretty simple. Remember, they're going to give you a delta t that's equal to 0.5. Give me a second, this pen's giving me S. A delta t that's equal to 0.5, which means that every time you think about this initial curve, it's going to go 0, 0.5, 1, 1.5, and then 2. With all of that being said, then you have how many points? 1, 2, 3, 4, 5 points you need to take account for. Now, the next big important thing you need to remember is like the basic equation for trapezoidal rule, which is delta x. In this case, we can just say it's delta t because they give it to you, divided by 2, f of a, f of a plus the summation of 2 multiplied by the summation of f of a plus k delta x plus, I don't know why the hell it's doing that. We're going to just go to the other one. Plus f of b. Now, it might look a little ugly because for some reason my pen thing isn't really wanting to work with me. And we'll switch it to the easier one in the second. So with that being said, that's going to get you delta x is just 0.5 because we decided what it was, or it just told us what it was going to be divided by 2. F of a is the beginning term, which is just this. That f of a is simply going to be plugged into the equation. So 0 to the power of 2 is just 0, but we'll do it for completion. Then we're going to do every term in the middle, which is 2 multiplied by, we have 0.5 to the power of 2 plus 2, 1 to the power of 2 plus 2 multiplied by 1.5 to the power of 2. And then finally, f of b is just the last term in your whole set, which is going to be 2 to the power of 2. You plug that into any calculator you get, and you're going to get an answer of 2.75. And then your answer is just going to be B. So those first 3 questions aren't the worst. Now, with that said, we got to continue. And I'll see if I can get through a bunch of these. Now, the next question says a lab technician is preparing a chemical standard that has the following level of equipment and glassware. You have a volumetric flask. It's 100 mils per plus or minus 0.1. There's an analytical balance, 100 grams plus or minus all those significant figures, and a glass pipette that measures to that certain accuracy. That's going to become important because when we're talking about accuracy and in general, things like this matter because your company, it is important to know significant figures. So your company's paying for those extra zeros. Those extra zeros in an analytical balance cost thousands of dollars. So if you're going to give a number to somebody and you use an analytical balance and then you measure what a graduated cylinder and you tell them this is significant figures, the least accurate shit is what matters because at the end of the day, you're not using all of the decimals. It's important. Significant figures are important. Most chemical engineers don't use it, which is funny. Now, with that being said, you also have to read the second part of it where it says a technician first weighs out 10 grams of solid and dissolves them in 100 milliliters of water. So with that being said, 10 grams is being weighed out, obviously, in the analytical balance, which is going to have 10.000 grams. We're assuming it's 100% ideal where all those significant figures matter. How many 6 figures does it have? 1, 2, 3, 4, 5. Now he says he dissolves them in 100 mils of water. Now, where's this 100 mils of water being placed? Well, any smart chemist has their 100 mils of water in the volumetric flask where they're going to put everything to shake up. So it's going to be 100.0. And it is going to be mils. So how many? 1, 2, 3, 4. 4 significant figures. Then the technician dilutes 1 mil of the solution. So this is a solution, and we'll get to that in a second. Of the solution to 100 mils using best laboratory practices. Well, again, how do we do this? Well, the first step is knowing your basic chemistry. Let's start there. How do we calculate a solution? Or excuse me, how do we calculate the molarity of a solution? Is just grams divided by liters or moles divided by liters. It's mass divided by volume. So if we do that real quick, we'll get the initial part of the solution you need. So it's going to be 5 significant figures divided by this amount of significant figures. And you're going to end up getting something that needs 4 sig figs in total. Now, think about it this way. Why does it matter that we do this? Well, if you're going to dissolve something and you're going to do a solution to it afterwards and dilute it, you need to have a solution first. And getting the solution needs its concentration. So with that being said, there's 10 grams. That's 5 significant figures divided by 100 grams, which is 4 significant figures. And any chemist or anybody with a half a brain cell can tell you that when you're dividing and multiplying, the rules for significant figures is that it's the least accurate amount of significant figures. So in this case, which is least accurate, 100. It's the least amount of significant figures when you're multiplying and dividing, which is obviously in this case 4 sig figs. Now, when you're adding and subtracting, it's the least accurate place, which is a little bit different, but that's for adding and subtracting. In this case, we have 4 sig figs for the concentration that we calculated. Now, that's just doing this first part. Then the chemist dilutes 1 mil of the solution, which he uses in order to get that 1 mil of the solution. He needs to use a glass pipette. You pipe it out of the thing you just made from that volumetric flask. So the 1 mil of solution is going to be 1.01 mils. And you obviously that 1 mil of solution has a concentration that involves this, which is 4 sig figs. It doesn't really matter what the number is, but it's just how you do it. Then it's going to be equal to the new concentration of solution, which is technically what you're supposed to find. And he then dilutes the 1 mil of solution to 100 mils using the best laboratory practice. Well, if you're going to dilute it to 100 mils, you're going to have another volumetric flask as to what you're going to dilute it to that line. And that flask is, again, 100.1. With that being said, if you divide the 100.1, because you're solving for m, you're going to get a total of 1.001, 4 sig figs, a number with 4 significant figures. And the dog is fine, I promise y'all. He's just a puppy, husky, super loud and doesn't stop talking. He doesn't stop talking. We try to sleep. It's funny. Now, we also have 100.1. Now, let's do the same rules. This is multiplying and dividing. So what's the least amount of significant figures? Well, in this case, it's 3. So your final answer is going to have 3. Now, the solutions manual says 4, but I don't agree with them. And I think it's wrong because they say that this glass pipette has 4 sig figs, which is a lie because 1 mil does not have. They're saying that this in the solutions manual is 1.001, but it only has 0.01. So they're adding an extra 0. I think it's a miscopy. So I think the correct answer would be 3C. It's a little different from the solutions manual, but I trust my answer because I can actually explain it versus theirs where they're just like, it's 4 for no reason. Okay, that's the quick and dirty of that one. It's not too bad so far. Number 5, match the curve properties. What the hell is that? Number 5 says, match the curve properties with the correct locations on the curve shown below. Well, you have derivatives, you have a curve, and we want to match everything we can with it. Well, let's go quick and dirty. So you have A, B, C, D. Now, remember a couple of things. The first derivative, when it's equal to 0, when the first derivative is equal to 0, you can immediately think the calc 1 and you think the first derivative test. And what does the first derivative test give you? The first derivative test gives you relative maximums and relative minimums. It doesn't give you absolute max and absolute minimums, but it does give you maxes and mins of your curve, which is important. Now, with that being said, what does the second derivative test give you? Well, the second derivative test gives you concavity. And what does concavity mean? Well, concavity are curves that either point up or down. Now, the second derivative test matters because when it's less than 0 or greater than 0, it gives you concavity. So when it's greater than 0, you're concave up, which looks like this. And if it's less than 0, you're concave down, that looks like that. That's just basic calc. Now, with that being said, let's match it. So point A needs 2 of these properties. Well, obviously, it's a relative max. So it's going to go with F prime equal to 0. So it goes with A. We'll go F prime equal to 0. And it's also concave up. So we're going to go with F double prime greater than 0. Now for point B, we'll get to that in a second. But Dominic actually knew this question. What does B and D mean? Well, B and D look kind of weird, but it's an inflection point. And how the fuck do you get an inflection point? Well, you get an inflection point if the second derivative is equal to 0, which is good. And so these are 2 points of inflection. So immediately you know that this has to be F double prime equal to 0. And the same thing with the D. F double prime equal to 0. Now, with all of that being said, we are left with point C. And remember what I told you. First derivative test gives you pluses. It gives you maxes and mins. So the first derivative test here applies again. So it's F equal to 0. And remember when we talked about concavity. So it's going to be the double derivative less than 0. And here, it's just giving me shit. And those would be your answers. It makes sense because if you put it all together. Now, having it by itself doesn't do shit. Like, the power of the first and second derivative test is when you use them in conjunction, because then you can get absolute maximums and absolute minimums and basically define everything without really needing a graph, which is the powerful part of derivatives. And in case people don't know, the first derivative is just the first derivative is literally just slope. So that's the power of it. Anyways, I can go on and on because I really like math. So we'll go to plot the point on the log graph given below. Now this one needs I'm still a little bit not 100%, so we'll preface that with that. But I have my notes here, which I gotta bounce around because I have like 100 sheets. So in a log scale, you need to think about this. 10 to the power of x is equal to some number, which in this case, we're just gonna say that it's 80,000. Right? Excuse me, which is the same thing as saying is x is equal to log base 10. Excuse me. Log base 10 of 80,000. Now, the important part for us is that this is a log scale, and you can see that these are based on log the power of whatever. So do yourself a favor, and all you got to do is literally go on your calculator, plug this puppy in, and it's going to give you x is equal to 3.84. So in a similar fashion, then you end up getting 10 to the power of 3.84. The hell? 10 to the power of 3.84. You can do something similar for the y, and it'll end up giving you 10 to the power of 4.9. And now we just have to plot this on the actual graph. Well, we'll start with the x because that's the simple one. X is 3.84. So here's your 3. So now you just have to line it up. Now, it's a little bit weird how I figured out how to count this, because if you count it normally, like 1, 2, 3, 4, 5, you'll be off by a whole digit. And either the manual's wrong, which could be, but this is how I'm going to do it to match the manual. So this isn't 1 that starts. It starts 3, 4, 5, 6, 7, 8, 9. So your 9 is there. And this extra line, I'm going to say is 9.5. I don't know why, but it doesn't work if you use it 1, 2, 3, 4, 5, 6, 7, or 2, 3, 4. It starts at 3 for all I give a shit. And we'll run all these up. Now, similarly, similarly, so this is the y, and then this is the x. You solve them doing this both ways, and you plug and chug. Similarly, we need to talk about the y-axis, right? Same way you label it. It goes 3, 4, 5, 6, 7. You'll have an extra line at the end that makes no sense. But since this is the x, you start at 4.9, 3, 5, 6, 7, 8, 9. You'll have an extra line. So let's go 3, 4, 5, 6, 7, 8, 9. There you go. That's the 9th. You'll have an extra line before the actual to the power of 5. So that'll be your 9th. Similarly, here you go here. It goes 3, 4, 5, 6, 7, 8, 9. Now, it'll go right about here, and it'll be a little rough because I can't get that accurate on this page. It'll be right about there if you count that way, and that's all you got to do. That's the answer. There's nothing too complicated. I wish I could be clearer, but my YCOM is trash, and that's it. You just turn them into log scale and you plot them in like that. As long as you can read that, simple. Now, number 7 is fun because number 7 has the ability of tricking you, because we're engineers, not fucking statisticians. It says you have a fair coin toss and you toss 10 times, and the probability of getting exactly 4 heads and 10 tosses is most nearly how much? Now, I read an entire section of stats based on the book Chantel gave me, and I learned a lot. So shout out to Chantel. But let me see where they at. My notes here. I found it. Oh, wait, what is this? Give me 1 second, guys. Obviously, you can skip around until I find my notes. So I can go off the top of the dome, but I don't really want to, because I don't think that's a smart idea. Oh, there you go. Sorry, I have so many notes here. It's ridiculous. So for this, and I want to make sure it's right so you guys don't fucking yell at me later. We need to know a couple things. Well, first, we need to know what equation we're going to use. And we're going to use this equation you can find in the reference manual. It's a probability of things happening after over and over. It's P equals n to the power to the exclamation mark, which is a mathematician function, x to exclamation mark, n minus x exclamation mark. That right here is just a combination. That's what they call it. And then you'll go P to the power of x, and then Q to the power of n minus x, where Q can also be defined as 1 minus P, which is Q. Now, what is n? Well, n is the total number of units or total number, whatever that you're doing. In this case, n is equal to 10. Now, x is how many times you want to do something. So in this case, exactly 4 heads. So you're in this case, you exactly want 4 times of heads. So x is equal to 4. Now you have everything to plug and chug. Now P and Q, what the fuck are they? Well, P is the probability of something happening, and Q is the probability of it not happening. So P, in this case, is equal to 50% or 0.5 because it's a 50-50 chance of getting a coin toss. Now Q, like we defined earlier, is 1 minus 0.5. And since it's a 50-50 coin toss, you don't really even need to use the equation. You know it's 0.5. Now you plug everywhere in, you see that. So it's going to be, this equation is going to be kind of nasty. It'll be 10 to the power of I, 4, I, excuse me, not I, because that actually is different. 4 to exclamation mark, 10 minus 4, exclamation mark, 50% to the power of x, which is in this case 4, and another 50%, because that's the calculation, 10 minus x, or excuse me, n minus x, which is 10 minus 4, which is 6. It'll get you that. Then you plug this puppy into your calculator, and even the shitty calculators have the exclamation mark. You don't need to do anything crazy. And you're going to end up getting 0.2, and that's the answer is B. Nothing crazy. It's just that you've never seen it, so you don't know how to use it. Now, let's go here. Now, this one's annoying because you need to use something called a normal distribution table. And they have it in the reference book, which I didn't download because, you know, I'm a smart engineer. That's what I am. But basically, you'd go in here, normal distribution. And they should have the normal distribution curve right here. You do. So we'll get to that in a sec, and we'll need it somewhere here. Okay. And if you're Madeline, this is just review because we've seen this shit before in analytical chemistry. For everybody else, then pay attention. So suppose the length of a phone call, the length of a phone call form a normal distribution with a mean length of 8.0 minutes, which is important. The first thing you need to know is the normal distribution. So that should immediately tell you, oh, it's a Gaussian curve. And B, I need a normal distribution table, which we'll show you in a sec. And then it says it's a mean length of 0.8. All a mean length means is that mu it is equal to 8. In other words, it's just the average. It's just they call it mean length. It's just the average length, okay? Nothing scary. And a standard deviation of 2.5 minutes. Well, standard deviation in stats is a sigma 2.5. And then it says the probability that a phone call will be selected at random and last more than 15.5 minutes is most nearly all these options. So in this case, we're going to define 15.5 as x. And we'll get to every single reasoning for it in a sec. So you have 8, 2.5, 15.5. And we need to calculate a z. Now, this z is kind of like a standardization, so we can use the normal distribution table. Because as is, we have nothing to use that table. We need a way to get that table. And how do we get the z? The z is mu, which is your mean length, minus your excuse me. Let me write that correctly. I don't want to confuse anybody. So z is equal to, according to that book, x minus mu divided by standard deviation. So plug that in for yourselves, and you're going to get 15.5 minus 8 divided by mu, which is 2.5. Now that's going to simplify into an easy, nice answer, which is actually cool, which is 3. But you're not done. So you're like, okay, I got 3. What the fuck would I do with the z? So you go to your reference handbook, and you're going to go here to the normal distribution table. You're going to find this normal distribution table. And the one that matters, and the one you're always going to use, is going to be capital F of x. That's the only one you're ever going to need to use. This side, my mouse is on. So you calculate z, which is this table, which x. This is for a Gaussian distribution. We calculate z because we are not standardized to that x. We just standardized it, which they call z. So z is equal to 3. You go on this x column. You scroll all the way down, and you find 3. Now, you go to this column, which we decided was the one we're going to use, capital F of x, is equal to 0.9987. So you go back here, you go back to the drop button, and you're saying, according to that distribution table, you're going to get 0.9987. But that is not the answer. Don't get fucking fooled, because you would think the answer is D, but it's not. You're not done. It's one last step. You're going to do 1 minus the answer you just found in that table, which is 0.9987. And then your answer for the length of how many calls last longer than 15.5 minutes is actually 0.0013. And that is always how you use this table. Don't get fucking fooled into just, boom, I got 0.9998. Don't. Use the capital F of x, and remember, 1 minus whatever that normal distribution table gets you the answer. In this case, it is A. We learned that in analytical chemistry, and I retaught myself using that book that Chantel gave me. And I assume everybody else is going to buy. So, next question. Now, standard deviation of the population values of 1, 4, 5, and 7. So here's the thing you need to know. First and foremost, it says population, standard deviation of population. That is the most important thing to ever see, because there's 2 types of standard deviations. Standard deviation 1 is a standard deviation of a sample, which, in all honesty, a standard deviation of a sample means jack shit in this case, because that equation is wrong and it won't get you the right answer. And there's also the standard deviation of a population, which is the equation we're going to use. So again, you would go in your reference handbook and you literally Control F, standard deviation of population, it'll show up. But since I'm a beast and I have all of this shit written down, I don't need to worry about that. So number 9, the equation for standard deviation of a population is equal to giant square root 1 divided by capital N multiplied by the summation of xi minus the mean squared. Now let's talk about it. Okay, capital N is the number of things you're counting. In other words, anytime you see an N, it's just like the total you're using. So in this case, our N is going to be 3 because there's 1, 2, 3. 3 things we're using, N is equal to 3. Now, xi is just your simple number. Xi is literally 1, 4, and 7. And we'll show you how it's done. And U, or micron, I don't fucking remember the curvy U, sexy U, I don't care what the fuck you call it, is mean. In other words, the average. So how do you calculate average? I mean, everybody knows how to calculate average. That should be your first step. So we'll do it on the side. Mu is equal to 1 plus 4 plus 7. Divided by 3, because there's 3 total items, you get a mean of 4. Now, how the fuck do we use the rest of it? So it's going to be omega equals giant square root 1 divided by 3, big parentheses. So this is xi is 1, because that's the first term, minus your mean, 4, squared. Again, because it's a summation of all of these, xi changes to the next term, which is 4, minus your mean, which is 4, we calculated, squared, plus Again, xi, which in this case is 7. 7 minus 4 squared. Now, you being a super smart son of a bitch, you're going to type all of this shit into the calculator at the same time so you don't have to do 15 fucking steps. And this simplifies to the answer. Once you plug it all in, you plug it in correctly, you get square root of 6, which is beautiful. None of these are too hard. I promise you guys. It's just a matter of knowing what the fuck they're telling you to do. Okay. Now, I need to go and get my other pair of notes. See how hard I work for y'all? Do you see how hard I work for y'all? Okay. A rugged-sized thermocouple is used to measure process temperature and has a time constant of 2.5 minutes. Considering the thermocouple is a first-order system with a gain of 1 and the amount of time required to reach 99.9% of a new process temperature is most nearly what? Okay, there's a couple things going on here. It's the first kind of real chemical engineering question. First things first. Process temperature, time constant, 2.5 minutes, thermocouple, first order system. What the fuck does that sound like? Process control. So process control, first order system, you need to know two things. Anytime you talk about first order system in process control, you know your transfer function is equal to K divided by 1 plus S time constant. K is gain, T is time constant, S is just S, because, you know, Laplace, and 1 is just 1. Now, you also should know that in the time domain, because this is in Laplace, in the time domain, y of t, I fucking don't get why it's doing that. Y of t is going to be equal to k, so time, goddamn you, k multiplied by 1 minus exponential to the power of negative time divided by the time constant. So in this case, since we want the number of time that we're going to be using, we're going to talk about the time domain. You don't really need to care about this, but if you don't know this, then you're kind of fucked. Now we need to talk about what the question's actually giving you. Well, the question says that they give you a time constant that is 2.5 minutes. They give you a K, that's a time, that's gain, that is equal to 1. And they're saying that you need to figure out how long it takes to do 99.9% of the process. In other words, Y is equal to, because we don't use percentages, 0.999, divide by 100, because nobody actually uses a percentage. Now, you plug all of that shit in, but the first things first, you would plug all of this shit into your equation here and solve for t. Now, for you guys, I'm such a swell son of a bitch of a lad that you're going to end up getting, if you decide to solve this thing in terms of variables, natural log of y minus natural log of y minus 1, which is just the constant that you was given, divided by negative 1. You might be wondering where the fuck that negative 1 comes from. It comes from this e multiplied by negative t, negative time constant, is equal to t. I just solved this. You guys are engineers. You can solve a basic fucking equation. I just wanted to write it out. In other words, you're going to get ln of 0.999 minus 1 divided by negative 1 multiplied by negative 2.5, which is your time constant, equals t. T is equal to 17.3 minutes, obviously. Again, if you guys can't turn this into this, then talk to me and DM me, because that's not what should be hard. Knowing all of the other shit is hard. The algebra itself is not. 10 is done. I think we might only do 25 questions at this rate. I've been talking for a while and my voice is getting rusty. Ooh, free body diagram, number 11. So I don't have an exact answer, but I do have the explanation to how the fuck to make this work. So let's look at the free body diagram of this random thing that's on an angle, and it has this little like dot here. That little dot's important because that's touching a wall at two different places. We'll get to that. So obviously we have a couple things we need to take in mind. There's obviously a force here and a force here because the question is showing it to you. And there's going to be a force here because it's touching the table. And there's a force here and it's touching the roof. So let's quickly boost some logic. If the picture is showing you a free body diagram with two arrows pointing exactly where they're pointing, 9 times out of 10, these arrows are already filled in your free body diagram. So immediately, no matter what, since this is flowing up instead of down, get that shit out of here. This is going down and down, get that shit out of here. You see? This is not matching these two, so fuck those. Now you have two options left. Well, there's this pointing down, that's good. This is pointing to the right, that's good. This is pointing down, that's good. This is pointing to the right, that's good. Now, okay, obviously, this is touching the top wall here, and it's going to have two forces, but we'll get to that because most people won't remember that shit. I sure as fuck didn't. So we need to talk about this. Well, this is a floor, and it's touching this rod. But let's read the rest of it before we answer that. It says the weight of object is neglected, so there's no force to the ground. Which of the following is free body diagram? Think about it this way. This floor and this object have a touch. They're touching each other, but the floor is exerting a force onto the rod. But if the floor is exerting the force, that means the floor is pushing this upwards, which makes sense because there's a normal force from the floor to the rod. It's not going down because there's no gravity. This has nothing being pushed down. So this is moving up. Well, it clearly isn't going to come from the fucking side because the floor isn't from the side. You know what I'm saying? So get the fuck out of here. So your only option is C, but you guys aren't fulfilled with that answer. You are questioning, why the fuck does this top part have two fucking arrows? Well, let me tell you something. This little dot's important. Without that dot, there's only one force. With that dot, it's telling you that it's a contact force from both the sides and the top. Now, where those two arrows point is your guess is as good as mine. But you immediately know it has to have two forces because there's a dot there. If it doesn't have a dot, it only has one force pointing exactly up. But using process elimination, using your big brains, trying to actually think about this, you have this, this, and this. So the only answer could be this. Now, if you guys actually want to do more research and you can update it and make your own videos, I'm not going to do that. I'm just trying to get shit done, you know? Fast as hell. That doesn't necessarily mean you need to know everything. Okay. So number 12 and number 13, do you guys remember resistors? Do you guys remember any of that shit? I sure as hell do. So we're going to keep going. So where the fuck is my annotation? Annotate. Okay. So with that being said, we have to remember a couple things. Resistors in series, resistors in parallel. So if we're going to do this, resistors in series are simple. They just add each other up. They just add the equivalent resistance. Resistors in parallel are equal to R equals 1 divided by 1R plus 1R. What the fuck? I hate this fucking shit. Here, 1R, etc. Those are resistors in parallel. Resistors in series are just a simple R plus R, which is nice. Now, with those basics out of the way, these two are in series, so they add up, and you get to rewrite this puppy. And when they're in series, it then becomes another parallel branch. So 3 plus 3 is 6, so you have 6, 6, 6. That's easy, and there's a 2 here. Now, 6 plus 6 plus 6 are all in parallel because they're all pointing up and down. So then it's going to become 1 divided by 1 over 6 plus 1 over 6 plus 1 over 6. All of those are equal to total resistance. And then this rewrites again. This is 2. And all of this turns into, guess what? 2. So there's 2 and 2. And then these are, again, in series. And then the parallels just stay in parallel. Unlike these that turn into one straight line, they just stay in parallel. So 2 plus 2 is 4. And that's B. Light work. That one is easy. Anybody who took basic circuit shit, remember that. Okay, next one. The next one is the current value of I in amperes in the network shown below is almost nearly. So that's the question. What the fuck do we do here? Well, I like everything. I have like 1,500 notes, and I just need to make sure I have the right package. So give me a sec. I can do it, but I have it like all written out. I don't want to be that guy accidentally giving you fucking information that's wrong. So I'd rather have it fully written down double, triple check instead of going crazy. So 13 and 14 is going to be on this one. Okay. Yeah, I have so many papers. Okay, so how do you answer this? Well, first things first, you have to do uh Kirchhoff's laws, I think is what it's fucking called. Someone can Google it. You could do nodal analysis, circuit analysis. I'm just gonna use the simple analysis I know. Fucking follow the current. And there's a trick to it. Don't You can define current as ever however you want it. You can go against the grain or you can go with the grain. And what I mean by that is that you can define current going clockwise or counterclockwise. In this case, we're gonna go clockwise, I think. That's how the clock goes, right? It goes this way. Clockwise. And follow the current's rotation. And the reason we're going to do that is that then we don't have to worry about the sign at the very end. If you follow what the diagram gives you, don't worry about the sign, and whatever you get at the end is the answer. So let's follow I. So I is traveling this way. La, 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 la. It hits its first resistor. Resistor and I. So it's going to be 24 multiplied by capital I, because that's how I define my current. We don't know the value of current. That's what we're trying to solve for. Keep going. Resistor hits a plus 50 voltage. It's coming in at a plus. That battery is at plus 50. Keep going. And it's now going to hit 10 ohms. That's going to be 10 I. Keep going. It's going to enter this next battery at a minus 25 voltage. And then it finishes its curve coming back at plus 16. Comes back at plus 16I. And remember, since the closed loop, it's equal to 0. Now, combine like terms, and you're going to get 50I plus 25 volts equals to 0. Solve for I. You get negative 25 divided by 50, which is the same thing as saying negative 50% or 0.5. And that's the answer. It's going to be C. If you were to do this the opposite way around, if you would have made your thing anti-clockwise, you would get positive 0.5, but in your head, you need to know to turn that shit negative because you're going against the current shown in the diagram. They have to define the current in the diagram. If not, they can't have multiple choice answers because technically it wouldn't be wrong because it just you chose it wrong. It doesn't matter. Okay. For the vector R, 12-foot I, and 8-foot J, select the graph that shows both components and the resultants. Now that's easy. Anybody who went to physics and paid attention should know that this is the X component and this is the Y component. And they're giving you a free body, not a free body diagram, but they're giving you a graph and their resulting vector in all of these graphs. Let me scroll down. The resulting vector is either pointing up or down, and it's on you to figure it out. Well, I mean, luckily for you guys, they're giving you a positive 12I, which means 12 feet in the X direction. So your X component is going to move. Let me change its color to blue. Your X component is going to move plus direction into 12. So you have 12 feet here moving forward. Now, they also say minus 8 feet. Remember, vectors are fucking defined by tail starts the new line. So you have the head here, it connects to the tail. In other words, you have the head connects to the ass. That's the best way you can think about it. Head is the tail. Or there's a way of saying it. The head is the arrow that you end your X component on, and the tail is the ass of the next component. So watch. Your next component, the ass starts here. So you should make your line. This is negative 8. Now let me be more clear what I'm trying to say with that head tail shit. This is the arrow at the end, so that's the head, and it's touching the ass of the new line. In other words, they're best buddies. They're just, lovers. That's how you think about vectors. And how the fuck do you finish it? Well, that's not the resulting component. That's just two components. And again, to make life wonderful, you just close it. And you simply close it like this. Sorry, guys. I got distracted. You simply close it like this. Boom. and you call and give yourself a pat in the back, which is nice. Because the resulting R starts at the very beginning and origin and just connects the Y component head. Easy. Physics. Sorry, I got a little distracted there. It's a lot I'm going through. Okay. Okay, 15. It says 0.25 steel rod with a cross-sectional area of 1250 millimeters squared and a modulus elasticity E of 200 gigapascals is subjected to 500 Newton force shown below. The elongation of the rod is most nearly blank. Okay, first things first. You see the diagram? It's not a spring, so you can't use F equals negative KX. That was my first thought. Then you're fucked because you don't know how to do the rest, right? But the elongation of the rod is also deformation of the rod. So you go into your trusty FE supplied handbook and type in deformation equation, and it'll show up the equation you need to use. Since this is not a spring and you're forcing it to fucking stretch, you are deforming an item. So the equation used is deformation. And if you decide to do that, the equation that you end up going to get is delta is equal to P L A E. A is area, E is elasticity, P is newtons, and L is obviously length. And remember, in SI units, everything is easier if you just make everything in the right terms. So it's going to be 500 newtons, 5,000. Let me say words correctly. The length is L, but remember, 0.25 meters divided by area, which you can convert. So I'm just going to put the giant conversion factor here. For every mil, it's 1,000 millimeters. Got to square it because everything's squared down there. And then gigapascals are just 200 gigapascals, but you need to make sure they're in pascals. So it's 10 to the 9th pascals for every 1 gigapascal. Now, that's going to simplify into 5 times 10 to negative 6, put a positive 6 meters, which is the same thing as saying 5 micrometers. 5 micrometers. I fucking hate this pen. 5 micrometers. Which then the answer is C. Nice and easy. That's just an equation that's just basic. You need to just know that it's, since it's elongating, it's just deformation. I know, I didn't know that either, but that's the perks of going through this. Okay. 16. In general, metals with high hardness will also have which of the following characteristics. Now, Madeline, I expect you to know this. You're a chemist. But normally metals that are really hard, they have high tensile strength, high yield, high strength, high intermolecular bonding, which makes sense because metals are normally ionic, high impact, rebound, and scratch resistant. So all of the shit I just said, it would be intermolecular bonding, which is B, high tensile strength, high yield strength, and high absorption and scratch resistance. You sort of just need to know that. There's no in between. It kind of sucks. So you're fucked if you don't. Okay, so if an aluminum crisp a connector were used in a connection copper wire to a battery, what would most likely happen? Well, the answer is pretty simple. You go to page 65 in the PDF or 67 in the PDF, you're gonna have a whole table of corrosion. Or you could just do this. Corrosion of reactions. And they have a whole list, which is good. Now, the whole corrosion system here is sort of nasty, but the answer is going to be B, aluminum connectors will corrode. And the rationale for that is that aluminum is anodic compared to copper, so aluminum will corrode to protect the copper. Now, how the fuck do you know that? Well, aluminum in this graph here is this, and copper is Cu, which is this. If aluminum is lower on the list than copper, that means it's anodic. If it would be higher, it wouldn't be anodic, and copper would corrode. So because aluminum is lower on the list in this list here than copper, you know aluminum is going to corrode, and it will protect the copper. That is the simple way to doing this. There's no real explanations, if and or buts. I personally think I love that because they're self-explanatory. Okay, next one. Okay. Glass is said to be amorphous material. What does amorphous mean? Again, Madeline, you're a fucking chemist. Like me, I'm a chemist too. You should know this. In other words, amorphous materials are materials that have no crystalline structure. Okay, that's it. Just D. Everything else is wrong. It's just they have no crystalline structure. That's the beauty of it. Okay. Next, 19. 5 columns, C1, C2, C3, C4, C5, are labeled in the periodic table of elements, so columns that contain an element that could either have a plus or minus 3 charge. Now, I hate calling out Madeline, but she should know this easily. So think about it this way. Draw. In the periodic table, this is +1, this is +2, this is +3. Technically, this is plus or minus 4, because it could be either. Then it goes -3, -4, -2, -1. Okay, so first, which element can have a plus or -3? So it's going to be columns 3, or the one I circled, C4. And since it doesn't give you the option to kick the other one, which would be this column here, V. But if you ever need to know, technically the V column right here also would count, but they're not asking for it because it's not C4, C2, C3. It'd be definitely C4, just based on trends that I just labeled out in the periodic table. And it'd be C3. Now, why is it C3? Well, C2, C1, and C5 all have 1, 2, and -1 charges, so they're out of the picture. How about C3? Well, think about it this way. Iron, rutherfordium, osmium, and I forgot what the fuck that one's called. All are metals, and metals could have whatever charge you want to give them. Iron could be +2 or +3, and so could all of these metals be, because they're in transition. They can have whatever charge you want. So C3, because they could technically be a plus charge of 3. You've ever seen Fe Roman numeral 2? That's plus charge 2, or Fe Roman numeral 3. You just kind of remember that from chemistry. Like iron can have that +2 or +3 charge, and all of them in that row can do that too, because they're transition metals. That's the beauty of them. Cool. That isn't too hard to explain either. Just chemistry. If you need a review on that, ask a chemist. Now, double replacement reaction between silver nitrate, hydrochloric acid, which one of them would be the product in the reaction? Well, we need to know how to read. So silver nitrate, Ag plus 2. Excuse me. Aluminum, zinc, and silver. Aluminum is always a +3 charge. Zinc is always a +2 charge. And silver is always a +1 charge. Nitrate is NO3 -2. Excuse me, -3 charge. These are polyatomic ions. Nitride is written differently. And it's a different polyatomic ion completely. But I think it's still -3. There's a polyatomic ion sheet that I can upload to the drive once I remember. It's from high school. It's something you should remember. This can be written as Ag3NO3. Now, hydrochloric acid should be easy. Hydrochloric acid is just HCl. Double replacement reaction is take this and connect it to this, and take this and connect it to this. Always, no matter what. So Ag +1, Cl is -1, so it's aluminum chloride, plus H3NO3. Double replacement. Now, which one of these are the product? Oh, it's not chlorine gas. It's fucking wrong. Nitric oxide. I don't see any nitric oxide here. Silver hyperchlorate makes absolutely no sense. The only answer is silver chloride, as shown by the double replacement reaction. How is the solution of pH 2 prepped using 6 molar hydrochloric acid? Now, this is another one you need to know a little bit of chemistry for, but it's not too hard. If you remember, pH is easily going to give you a molarity of something. So pH of 2, you can do negative 10 to the power of negative 2, and that's going to get you a molarity of 0.01 molar. Another thing you need to realize is that you need to calculate the molarity, which is pretty obvious. But also read if you need to calculate the molarity, you need to know to use M1 V1 equals M2 V2. That's the obvious part. Now, what's not so obvious is that what is M1, what is V1, and then what is V2 and what is M2? Well, M1 is obviously this molarity and M2 is obviously this molarity. But what about V1? Well, look at all the questions. They're all using 1 liter of water. So M1 is 0.01, and they're using it of the hydrochloric. They're using, M1 is from the HCl, which is 6 molar. Wait. I'm getting my words confused. Excuse me. They're diluting the HCl solution, and they want to make an HCl solution of 0.01, which is your M1. The way they get this is by diluting this using 1 liter. You're looking for 6. That's your M2 of X. X is the volume used for diluting. X is equal to 0.0016 liters, which is the same thing as saying 1.6 milliliters. Excuse me. I had a lot of word salad there, so let's explain that. So negative 10 to the power of negative 2 is equal to 0.01 molar. 6 molar is what you're starting with, or you're preparing it using that. Now, you know that you're going to use a 1 liter flask that has a concentration of 0.01. So a total volume of that flask is 1 liter that has 0.01 of that solution. Now, the question is, how much do you need to use to dilute that into that? We'll just solve for X. That's it. Okay. Number 22 is fun. Number 22 is fun. So we all know that in organic chemistry, if you're a chemist, you should know all of these. It goes methyl, ethyl. So for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of those. They're methyl for 1, ethyl for 2, prop for 3, bute for 4, pent for 5, and hex for 6. Hex for 6, and then technically you could say hept or sept. It depends on the book, but most people use sept. Oct for 8, non for 9, and dec for 10. Now, what about 10 or anything higher than that? Well, most organic chemistry books don't tell you that. So in a carbon chain, you can also have undecane, which would be 11, and dodecane, which would be 12 carbons. Now read the question. A number of hydrogen atoms in a molecule of dodecane. Dodecane means there's a chain of 12 carbons. So draw your 12 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, you also have to fill in the octet rule, so make sure 1, 2, 3. Every single carbon has a total of 4 bonds, no matter what. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3. Now all of your carbons are happy. That's what you want. They all have octets. Now, do yourself the favor, and every single line represents a hydrogen. So this would be 1, 2, 3, etc., etc., etc. Count them all up, and your answer is going to end up being D, a total of 26. There's also an equation. If you remember alkanes, I don't remember the equation exactly. You can Google it if you fucking want to. It takes 2 seconds to do that, though. Okay. Number 23. It says, which analytical equipment provides the best method to analyze the mercury concentration in parts per million in ground sample? Well, gas chromatography. If you work at OroChem, you should know this. Son, Chantel, and Dominic, and including myself. So gas chromatography. It's just literally HPLC, actually. It separates and analyzes compounds that could be vaporized without decomposing them. In other words, it just vaporizes them and separates They won't destroy the molecule itself. That doesn't give you shit about concentration, though. It just tells you what it is. Now, viscometer, I don't really need to guess. You know what viscous is. Viscous measures the viscosity of a liquid. That's what it is. Atomic absorption unit. An atomic absorption unit is a technique for measuring the concentration of material elements in different materials. Ooh, concentration. Now, you probably think that's the answer, right? I would agree. X-ray diffraction is used to assess crystalline assess the crystallinity and the structure of a solid sample. We actually tried using that when I did the boron nitride research back in Dominican, but what ended up happening was that COVID, and I never got to play with it, which is to this day one of my saddest moments. Okay. Number 24. Oh my God. I might do 25 and end it into another 25 next week. I've been talking forever. Okay. I think that's what I'm going to do. The balanced chemical equation of molecular weights for reactant products and aerobic digestion organic materials are as follows. Data chemical equation, they give you the compound and the molecular weights in the table. Then they say the weight in pounds of methane produced for 2,000 pounds of organic materials would be most nearly blank. Okay. Y'all remember stoichiometry and basic chemistry? So you're starting with 2,000 pounds of, fuck you, not you guys, the stupid pen. 2,000 pounds of organic material, which is this bullshit. And you need to convert it into methane. If you know basic orgo, it's this. How do you do that? Well, you turn pounds to pound moles and pound moles to pound moles of the other object, and those pound moles back into that. That made absolutely no sense if you don't know what chemistry is, but it's easy. This is of orgo. There's 2,000 pounds of the organic material. First things first, you need to use the molecular formula. So for 1 pound mole of orgo, you get 1, 4, 3 pounds of orgo. Now you need to turn the pound moles of the organic solvent or the organic whatever into methane. So for 32 pound moles of methane, you know, I fucking hate this pound. For 32 pound moles, there's 1 pound mole of orgo. And see how everything cancels out, you're left with methane. Now, one final touch. What's the molecular weight of methane? There's 16 pounds of methane. God damn. This pen is so ass. Okay. For 1 pound mole of methane. And then if you type all of that into your lovely calculators, you'll get 714 pounds of methane. Again, I'm so sorry if you guys are hearing me struggle with this. It's fucking annoying. All right, number 25. God damn. All right, boys. Okay, number 25 is easy. The thing with 25 is that you just have to kind of know what yeast, well, not really yeast, but what the fuck the fermentation process looks like. So in the production of wine, yeast, grape juice is fermented in special tanks and equipped with pressure relief valves. These pressure relief valves are used to prevent overpressurization of which of the following yeast reactions? Well, the general products of fermentation are C2H5O. That is just ethanol, and carbon dioxide. With that being said, read all the questions. Produces gas, oxygen gas? No, because there's no oxygen in the product of fermentation. Carbon dioxide in fermentation? Okay. Carbon dioxide and oxygen? There's no oxygen in the fucking product, so the answer is C. Okay. Now, for number 26 is another easy one. These are 3 points. I'm going to keep going with the easy ones. I think I might stop with 26 because my voice is getting... Yeah, we'll stop with 26 and then we'll start next video with 27 through the rest. So 26 is warm water for 525 Celsius, the specific gravity of water. What does it do? Well, the specific gravity is calculated by... You have the density of the new stuff the new temperature versus the density of the reference temperature. So you go into the reference manual and you just get the densities of the water at those different temperatures. You type it in. I am not going through the book. That should be something easy. And you'll get that it's 997.05 kg. God damn you. Kg per meter cubed divided by 999.3, same units, and you plug that shit in, and you're gonna get 0.997 specific gravity. Circle that shit in, and you're done. Okay, I could keep going because the next couple are not that hard at all, but my voice is raspy, and I haven't done this in a while. My back kind of hurts. I think it's been about an hour. So, Madeline, Chantel, who else is here? Son and Dominic. I will try to upload the next 25 of these next weekend after I work on this a little bit more. I actually have all of it done. It's just, I'm tired. I don't really want to do this. Saturday or Sunday. I need to shower and do other things. So, with that said, and for anybody else who sees this, so if like multiple people have access to my drive, you want to use these to study, go for it. Anyways, I'll see you guys in the next video unless I somehow die. So I love you all. Bye.